Okay, so I guess for our clicker question 1. This is a little too fat for my taste. Oops. Push palette. Okay, so let me just reset this. All right. Okay, so clicker question 1. Okay, so the way your clicker points work. So please, this evening or tomorrow or something. So after around 5 o'clock or something, I'll upload all of your clicker scores. Okay. Please make sure you're getting points on for your clickers. Okay. So it'll show up on CCLE under the grade book, and then the way it works is there is 1 participation point per session, and then 1 point per question asked. So if I ask 4 questions, there's a total of 5 possible points. Okay, you'll get 1 point just for clicking a button some point during the day. Okay, and if you answer all 4 questions wrong, you would get 1 out of 5 points. All right, if you answer all 4 questions correct, you will get 5 out of 5 points. Okay, does that make sense to everybody? All right, good. So, okay, so clicker question 1. Let's try one of these out. Okay, so this will be true, false. Okay, true or false. So, standard true, A is true, B on your clicker will be false. And we will say true or false, placebos can be used in our observational studies. Okay, so let me just see here. Okay, so so you should be able to click, and I am seeing people clicking away. We've got 70 responses, whatever. Okay, all right. We'll say, I don't know, give you another 10, 15 seconds for this. It's either a yes or a no, okay? So we'll say 10 more seconds to get your clicks in. Somebody clicked the letter E. 1 person clicked E. So, you can always, so if you have the one with the screen, it'll tell you like what you've clicked. Okay, so I'm gonna go ahead and stop the thing. So, I'm sorry, I don't know who clicked a E. You never corrected your mistake, so you'll at least get your participation point, okay? And so here is our answers, and indeed the correct answer is B, okay? So, there's no reason to use a placebo in an observational study. Okay, the only reason why we use placebos is to control whether a person knows if they are the only reason to use placebos is to prevent the participant from knowing which treatment they are receiving. And in an observational study, there's no really assigning of treatments, so there's no need to prevent people from knowing what treatment they're receiving. Okay, so placebos are really only used in experiments. Okay, cool. So that worked. We'll have a couple clicker questions, I guess, throughout the lecture. So stats 10, lecture 3. Actually, it makes more sense to say week 3, Monday. And this is slide 1. Okay. Okay, great. So we left off on Friday's lecture talking about numeric variables, okay, and the relationship between numeric variables. I guess I'll throw that on. And then so we have, okay, so we're continuing on in chapter 4. Okay, so we talked about describing a relationship between two numeric variables. And we said there are three aspects that we should describe. Okay? Three aspects. We have the direction or trend. We have the strength. And we have the shape or the form. Okay. And we said direction or trend could be, you know, positive, negative, or neither. You know, the strength goes anywhere from weak to strong. And then the shape, we said linear or nonlinear. Okay, and I forgot for a second. Sorry, all right, and then okay. So we have a numeric summary. We have a sample statistic or a numeric summary that basically captures parts 1 and 2. Sample statistic. Or, you know, a numeric summary that tells us the direction and strength of a linear relationship. Okay? And so this sample statistic is called the correlation. Okay? This is the correlation. Or the full name is the correlation coefficient. The correlation coefficient, and the symbol is R. Okay, so the correlation coefficient has the symbol R, and it tells us the direction and strength of a linear relationship. So I'm going to give you kind of the interpretation of R, and these interpretations only work if the relationship is linear. But R is just the result of plugging some numbers into a formula, and so you can get R calculated for any data set with two numeric variables. Okay, it's just that the interpretation of R only makes sense if the relationship is linear. R can exist for nonlinear relationships, it's not meaningful, okay? So R can exist for nonlinear relationships. Okay? But will not have a meaningful interpretation. Okay. Interpretation of R only works for linear relationships. Okay, so let's talk about R, this correlation coefficient. Okay, So R can be any value between -1 and 1, okay? All right. So the sign of R is the sign of the direction, okay? The sign of R is the direction of the relationship. Meaning, you know, R positive, you know, if R is positive, the relationship has a positive direction. All right, and then likewise, if R is negative, the relationship has a negative direction. But I think you guys can figure that out. Okay, and the strength, okay, or I'll say R, if R is close to 0, the strength of the relationship is weak. And if R is far from 0, so, you know, close to +1 or close to -1, the relationship has a strong, the relationship is strong. Okay. One thing to note is that R is unitless. Unitless, okay? So, you know, changing units. So changing units, so like changing from feet to centimeters, or, you know, dollars to whatever, cents or whatever, okay? Changing units will not affect R. Okay, so changing units is essentially generally just multiplication or addition, you know, adding or subtracting or multiplication, you know, so adding or subtracting a constant or multiplying by a constant basically will not affect R. So adding or subtracting a constant or multiplying by a constant. Okay, so those will not affect R. Okay, so let's try this out. Okay. All right, so here's an example. So this is an example where this is supposed to be a perfectly straight line. Here, the direction is positive, right? Direction is positive. No scatter. No scatter means what? Strong relationship. So what is R in this case? R is equal to +1. Okay? All right, so here's a question for you, and the question is, and so this will be clicker question 2. Okay, so your answer choices are R is, A, R will be equal to 1. B is R is positive but less than 1. C will be R is 0, and D will be R is negative. Okay, all right, so give me a second. I'm gonna have to fire up the Okay, this is supposed to be a straight line, okay? All right, so go ahead and fire away. So I should say straight line, no scatter, I guess. Your question?
When you mean straight line, do you mean like a horizontal line?
No. It's definitely not flat, right? So straight line, and it's supposed to be like these line up in a straight line, okay? All right, so just a few more seconds, okay? So get your clicks in. Get your clicks in. Again, the clicker questions are intended to be, a little bit tough, get you guys thinking, and then we can discuss exactly the meanings of this, all right? Okay, so 5, 4, 3, 2, 1. I'm gonna hit stop here. Okay, let's see how you guys chose. Ooh, all right, so this is, the class is split. So this is a sign of a good question, all right? Okay, and the answer choice is A, R is +1. Okay, so again, the key here, all right, and I tried to give you the clue, is it's straight line, okay, straight line, no scatter, okay? So remember, and you might say, well, the slope changes, right? So over here, you've got, this is definitely less steep, okay? Less steep, but there's still no scatter. So as far as the strength of a relationship goes, it's a perfectly strong relationship, okay? So R only measures the strength and the direction. It does not tell us anything about the slope, okay? So R is equal to 1, okay? Is this okay? So, and again, on the previous slide we said R is not affected by multiplication by a constant. Okay, so really just changing the slope of a line is effectively just multiplying the values by a constant. Okay, so I hope that's okay. Yes, a question. When would it be positive less than 1? Okay, so that's a very good point. Well, I will draw an example of that, okay? All right, but I want to just make sure this is okay. Changing the slope of a thing does not affect R. R only measures the strength, and in both cases, the strength was equally strong because there was no scatter, right? So the strength of a relationship, the question is, how much scatter is there? Or, how well can I make predictions? And in both cases, there was equally 0 scatter. You can make equally good predictions. Okay, so when is R positive but not equal to 1, okay? And so here's an example where you've got some scatter. And so in a scenario like this, R would be, I'm making up a number here, maybe 0.85, okay? So you've got some scatter, not a ton of scatter. And this is what the correlation would look like there, okay? And meanwhile, okay, so what would this line have? R would be, R is -1, exactly, okay? And this would be what? R is negative point, I don't know, I'm gonna just say -0.8, okay? I have no idea, all right? But it's something to show that there's some scatter, okay? And as as we have more and more scatter to indicate a weaker and weaker relationship, R gets closer and closer to 0. Okay, so I'm just going to draw some other things here, all right? So this will be like to indicate lots of scatter, but still maybe overall there's a positive trend, I guess, of some kind. And here would be R is equal to, I don't know, 0.3, okay? This is just a guess, okay? But something to say, you know, positive trend, but, you know, lots of scatter. Okay. What about this one? R is 0, okay? Even though it's a straight line, it's neither positive nor negative. Flat, right? So this is flat, neither positive nor negative. So R is 0. All right. Is this okay? Good? Okay. Okay, so let's you tell me if which value of R seems most appropriate for the following relationship. Okay. So this will be a question. Okay. So we'll say R is greater than, you know, 0.9. Okay, so this will be, you know, strong. And then B will be R is, I don't know, between 0.6 to 0.8. C will be R close to 0. D will be R is this doesn't make sense. Okay, so so this would be question 3. Okay, so this will be X and Y. Okay, so X we will say is sorry. Okay, so assume a linear relationship. All right, so X will be outside temperature. And Y will be sales of sweaters at a department store. Okay, so we'll say dollar figure. Okay, so this will be on a day-to-day basis here. Yeah. Huh? Where are the temperatures being recorded?
And where are the sweaters being sold?
Los Angeles? I don't know. Oh, okay, all right. Maybe this is just a bad question. All right, well, right, so I guess we'll say like one record. You can discuss one record per day. Temperature is recorded where the sales are made. Okay, temps are recorded at the place of the sale. So I guess it'll just be outside temperature. The average outside temperature of the day. Okay. And then this will be like sales of sweaters at a department store for the day. I didn't think this was that terrible, but whatever, we'll see. Okay. Okay, we'll say 10 more seconds. So when this hits 2 minutes and 30 seconds, I'm going to stop the clock. Okay, get your clicks in. 5 more seconds. Okay, and I'm stopping here. Okay, I would argue that okay, so X will be the outside temperature, right? Okay, so this is the temperature, and Y is the sales, okay? So I'm just thinking, let's say it's 100 degrees outside. Am I going to be selling lots of sweaters that day? No, okay. Now, because we're getting different, there could be a clearance sale on a 100-degree day temp, or something. So, some days I might sell more or less, okay? So I'm expecting, and then on days where it's cold, let's say it's, 30 degrees outside or something, am I going to be selling more sweaters? Yeah, probably. Okay, so I'm expecting something, but then again, I'm expecting a fair amount of scatter just because the behaviors of people and how much you're going to sell at a store is, I would say, rather unpredictable. Okay, and so I would say something like this, and so my answer choice was going to be answer choice D here. Okay, so let's see. All right, so I saw some people high-five each other. This R, like greater than 0.9, or this very strong stuff, I would say, is reserved for things where it's generally really strong relationships. I don't know how I would say this. So I suppose, I can't imagine sales and outside temperature being kind of the only factor in determining the amount of sales, okay? So you generally only want to use really strong relationships of, R greater than 0.9 or less than negative 0.9, where it's really clearly like just there's only one thing that goes into determining the Y value, okay? So if it's like, I can't think of something, but just, I don't know, like for a certain species of snake, the length of the snake and its weight, I think, those are going to be very, very closely related just because, if the same species are probably all going to have about the same, whatever the thickness of a snake. So I'm thinking that's going to be the only real factor there. Okay. So that's what we have here. Okay. Is that all right, talking about correlation and all of this stuff? Okay. So the next part of Chapter 4 gets into modeling a relationship, okay? Okay. Okay, and so in modeling a relationship between two numeric variables, oh, you know what? I'm sorry. I apologize. I have to go back and just say a couple additional points about correlation. So we'll come back to this. Okay. All right. So a few more notes about correlation. I apologize. Okay. Switching x and y. Will not affect R. Okay, we already talked about adding a constant or multiplying a constant to either x or y. Does not affect R. Okay. Switching x and y, okay, and adding and multiplying by constant to x or y does not affect R. Okay. Yes. All right, so you can just throw that back in there for correlation, and that's that. Okay, so modeling a relationship between two numeric variables. Okay, so here we are trying to create a linear relationship between, or model the linear relationship between x and y with an equation for a straight line, okay? So we want to model the linear relationship with a straight line, okay? And so what is the equation for a straight line that you guys learned back in algebra? Y equals mx plus b, right? So from algebra, we say the equation of a straight line y equals mx plus b, okay? In statistics, we have the same type of thing, except we changed the letters. All right, and I apologize that we've done this. Yeah, I know why we've done it, but this is what we've done. Okay, so in statistics, we have this is called y hat. It's got a little roof over it. Y hat is equal to a plus bx, okay? So back in algebra, this was the intercept, and this was the slope. In statistics, this is the intercept, and this is the slope. And essentially what we are saying is that y hat represents our prediction for y, okay? So y hat represents our prediction for y. Okay, so what we're saying is, y hat equals a plus bx represents that when we plug in a value for x, I can get a prediction for y. For a particular value of x, I can make a prediction for y. Okay, and the value of that prediction, y hat, is equal to a plus b times x. Okay, this is essentially what we're saying. Now, this stuff only works if the form of our relationship is linear. Okay, how can we tell if the form of our relationship is linear or not? What's that? Yeah, we create a scatter plot and we just look at it. Okay, and that's how we tell. So we create a scatter plot and we look at it. So you know, this relationship stuff, it's called linear regression is the name of the analysis technique. Okay. Okay, you know, it only works for linear relationships. Okay, and you know, to see if something is linear, we create a scatter plot. And look. Okay, so we have y hat is equal to a plus bx. All right, and there's this question of, you know, what is the line? What line can we use? So let's say we have data that look like this, and there's a question, you know, is to summarize this data, should I use this line? Is this the right line? Or is this the right line? You know, I think it would be clear that, you know, this would not be a good line, okay? So we can say, you know, this line is no good. So blue line does not summarize. Like if we just wanted to kind of summarize the relationship between x and y for these 4 data points, we would say the blue line is no good, right? Okay, but there's a legitimate question of, you know, is the green line any good? What about the red line, okay? Which line is better? Okay, green or red? Because they both seem to kind of capture somewhat of the relationship, okay? Okay, so the best line, we will define the best fitting line as the least squares line, okay? So our best fitting line is the least squares line. Okay, and what do we mean by least squares line? Okay, what we're going to do is we're going to say, okay, let's take the line that you have used and let's see how much error is produced by the line. Okay, so how much error? So the error is basically how different was an actual value from the predicted value. Okay, so, you know, let's look at the line. And see how much error exists in the line. Okay, and the error will be the difference between the prediction we've made and the actual value. So another term for error is also the residual. So the error is also called the residual. Okay, but that makes sense, right? We just want to know, this is what I predicted. What was the actual value? And if my prediction was the actual value, then that was a good prediction. If the prediction was way off from the actual value, then I need some improvement there, okay? All right, so let me just kind of illustrate what this looks like, okay? So let's say we have x and y. I'm going to just have 1, 2, 3, 4, and 2, 6, 4, 8. These will be our values here. So, I don't know. Okay, so here is here's one plot. Whoa, something, that is not what I want. Okay, Lasso, you are giving me a hard time. One more try. Oh, okay. All right, never mind. I'll just draw it again. 1, 2, 3, 4, 2, 4, 6, 8, okay. Something like this, okay. So let's say my two candidate lines, so I'm gonna have this. So in this case, I've got y hat is equal to 2x, all right? And then over here, I'm gonna have y hat equal to 1 plus 1.6x. And that looks like, let's go with the red line. Something like that. Oh, I'm going to run out of time. Okay, well, we'll have to continue this in a little bit. Okay, let me just do this for this one. I think we have time for that. Okay, so basically, under this equation, the y hat, when I have x is 1, 2, 3, and 4, y hat will be 2, 4, 6, and 8, right? And so for the amount of error for x equal to 1, if I compare y hat to the actual y, which was 2, 6, 4, and 8, the error, which I'm just going to have e, for this one there is 0 error, and then for the last one there is 0 error, right? But then for x equal to 2, the actual value is 6, so the amount of error I have there is 2, and then when these, my graph is not good, but over here the amount of error I have here is -2. Okay, so according, when x is 3, according to the line, I'm predicting a value of 6. Okay, in actuality, my value was 4. Okay, when x is 2, I'm predicting a value of 4, but in actuality, my value was 6. Okay, and so we can measure the amount of error that we have, and we'll finish this story and example up on Wednesday. Okay, but here we're getting into the idea of modeling a relationship between x and y. Okay, so I'll post the results of the clicker up on CCLE tonight, so please make sure your clicker is working and you're getting points as you should.